Good day, guys. Alright, so what I want to do in this video is to begin with physical optics. Right, we'll start with Huygens principle and look as to how to apply it, and exactly what the model is talking about. Right, so this is going to be an advancement in our exploration for the nature of light. Light has two nature. Number one, the wave, as a wave, and then the second one, light as a particle. So we'll explore light as a particle further on later in chapter 9, but for now let's look at light as a wave. Right, so let's begin with Huygens principle, and then let's look at what Huygens principle actually says. Okay, so let's begin with, all right, so what does Huygens principle say? Huygens principle say that each point on the wavefront acts as a source of secondary wavelets that spread out in all directions in spherical waves with a speed equal to the speed of propagation. So generally, when you read Huygens principle, what you find is this particular picture. All right, so how do we translate from this statement into this picture, right? How do we translate that? Well, when they talk about each point on a wavefront, we're talking about this wavefront, the yellow one, the second ring, right? And then each point of it, right, if we take a certain point, say this one, they act as a source for secondary wavelets. So these are what we call secondary wavelets. Yeah, secondary wavelets in all directions. As you can see, they move in all direction, right, in spherical waves with a speed equal to the speed of propagation. Okay, so how the third wavefront is formed, we will have to explore what we call interference. Before we can explore interference, however, we have to explore what does it mean for two waves to be coherent. Okay, so let's look into that. So first things first, what is coherence? When we talk about two waves are coherent, what do we mean? Okay, so if we look at the slide right now, we can see that, okay, there's a bunch of words, it says exactly what it means, but the main point is that the phase difference between two waves stays constant. Okay, so and stays constant compared to what? With respect to time. This is a very important condition for stationary interference. Of course, again, we need some, how should we say, we need some graphical representation, or at least we need some visualization. So let's look into that. Okay, so here we have Desmos. It's a graphing calculator. It's very good. I highly recommend it. Right, okay, so what do we mean by constant phase difference? Say we have this wave, right? This is a wave. It will move to the right, right? And then we compare it to another wave, this one, right? And as you can see, their phase difference is always the same. They always differ by pi radians. This is very different when we compare, right, with this one. See, at certain point, if I stop at any point in time, here, they're almost in phase, and yet if I move it a little bit more, I let it move a little bit more, they're exactly anti-phase, right? So the phase difference between them here is going to be pi, and then after some time, here, it could be closer to 0. So in this particular case, we say these two waves are not coherent. Whereas these two waves, they're always pi radians in phase difference. Right? Then we say that this is this is coherent. These two waves are coherent to each other. Okay? Alright. Moving on. Okay, so now you know what coherence means. Okay, so once we understand that, okay, then we start talking about what's the other condition for light interference. The other condition, which is something that you have covered before, is what we call monochromatism or monochromatic, that they have to be of the same wavelength. Okay, this is what we require for a stable interference pattern. Okay, so these are the two conditions for a stable interference pattern from light interference, which is number one, the coherency, number two, the monochromatism, or at least they have to be monochromatic. Okay, generally in real life you will have monochromatics when they come from the same source, or you can tune two lasers so that they give out the same wavelength or same frequency, so that then you will have monochromatic lights. Okay, so once we understand that, then we can talk about constructive and destructive interference. Okay, so let's talk about that. Again, I will be using Desmos. Okay, so let's look at another visualization on how you can have constructive and destructive interference. So here I have a wave. Now, if this wave, right, is coupled with another wave, then what happens is that the interactions between those two waves will result in another wave, right? So here's the blue one and the red one, right? Those two waves, they interact, and then what they give us is the resultant force. And as you can see, the resultant force will have double the amplitude. So what we can see here is that the red one, the amplitudes of the red one, the red wave, and the amplitude of the blue wave, right? They add up. They construct on top of each other. And then what happens is you have another wave, the resultant wave will have an amplitude double of its components. Okay? Alright, so what about destructive waves? Well, I can get destructive wave by simply introducing a phase difference of pi. Okay? So what I can do is I can have the red one, then have another one that is shifted by pi radians. Then if I add them together, which is the results of this one, right? If I add them up together, they cancel each other out. And all I'm left with is this black line, because they cancel each other. Okay? So what can we say from there, right? What can we say from there? So what we can say from there is, for destructive interference, right? The condition is that the phase difference between them must be n pi. They must be shifted by n pi. Okay, so say you have pi, and then 3 pi and 5 pi. So there you can say, all right, n has to be 1, 3, 5, and all other odd numbers, right? So up to infinity. As long as they're odd numbers, then what we have is going to be destructive interference, and we can test it out. We can test this out, right? We can definitely test this out. Let's look at our graph again, right? So if I have the resultant wave here, if I simply put, okay, what if I have 2 pi? Then they just add together. What if I have 3 pi? Again, I have destructive wave. What about 7? What about 9? What about 11? Right? And so on and so forth. As long as the number, right, or the multiplicative for the pi is odd, right? It's an odd number, then what we will have is going to be a destructive interference. Now, for the constructive interference, what we want is that the phase difference between wave 1 and 2, right, is going to be again either 0 or n pi, where n, this n, is going to be 2, 4, 6, 8, and so on. All right. Again, we can test it out again just for demonstration purposes, right? Just for demonstration purposes, we can test that out. Sorry, 2, right? 4, 6, 8, 10, right? So as long as they're even numbers, then we will have constructive interference. Okay. Okay. Right. Moving on. So how does these two ideas, that Huygens principle, it becomes the wavefront, each point of a wavefront will become a source of another wavefront, and this interference, this idea of interference, contribute, right? How let's apply that. Let's apply that information. Okay. So say we have a point source. Again, we have the same picture again here, right? We have this wavefront here, the initial wavefront, and we want to determine the position of the next wavefront, next position, right? The consecutive position. So what we can do is we can set these points and then draw these sort of wavelets and see where they constructively interfere. So these points are going to be where they constructively interfere, and that constructive interference is going to form your next wavefront. Okay, so that's the idea of Huygens principle. Okay, or at least that's the application of it. Now let's apply it to a parallel. So let's apply it to parallel waves instead. Again, I have the initial wavefront, right? And I choose points and draw wavelets for them. Take notice where they intersect, right? And then where those intersect, you can draw another line joining them up, and that is going to be your new wavefront. All right, so that's how you apply to parallel waves. Now, can we have more complex structure? Yes, we can. We can have them through a slit. Okay, so again, we have a just a straight line, a parallel wave, and then as it travels, it reaches the slit. Once it reaches the slit absorbs that section of it. So this section is going to be absorbed, right, by the this section is going to be absorbed by the structure, and then what you're left with is this small part of the wave that becomes the new source. And from there, you can draw out, again, those small little wavelets and join where they constructively interfere. Alright? So that's where they constructively interfere. But what about this part? Well, this part is going to be absorbed. This part is going to be absorbed. And what you're left with is this curve of a wave for this side as well as this side. So then what you're left with, what you're going to have is a wave that sort of bends, right after the slit. Right after the slit is going to start bending. And this bending, this phenomenon that we describe as the bending of light after going through a slit, is what we call diffraction. Okay? And we will talk about that in the next video. For now, thank you.